Good morning, class. Today is September 23rd, and this is the lecture for 9/24. And we've been talking about chemical energy mined from the earth, otherwise known as hydrocarbons. And we've discussed petroleum. You can see on the chart there, petroleum is our largest component of energy that we use. And what we've found is that petroleum and natural gas are alkanes, and so they represent chemical energy in the earth that's been really sort of fully refined, meaning the organic matter that it came from has been sort of fully processed all the way down to these very simple single chain molecules. And today we're going to start with coal, which sort of it's along the line here: petroleum, coal, natural gas. Coal is, as we'll see, a completely different entity, and to a certain extent, we're sort of diverting away from the whole alkane picture, here. But part of the reason I do this is because it sort of provides you this perspective of the organic origins of all this stuff. Now, as you can see, coal over the years, and if you saw this chart, going back 10, 20 years, this number would be a lot bigger. Coal is kind of half as much as natural gas and petroleum, and we'll sort of explain why that is as we go through this. And the primary use of coal is in generating electricity. All right, so all about coal. And I never thought in a million years that I would ever be giving a lecture on coal, but here it is. So as I've discussed, coal is kind of it's of course buried organic matter, and we can talk about that a little bit. But the thing you have to understand is that it's not, well, I guess the easiest way to think about it is that it's not buried as deep, and so it hasn't undergone the full processing, so to speak, that occurs due to like with petroleum, natural gas, which are much deeper. That full processing of squeezing down this organic matter to simple alkanes, and so coal is much closer to the surface, and and so if you look at it chemically, you would see stuff like this, which looks a lot more like organic matter, and so it's a lot closer to the original organic matter, and that sort of clues you in that all this stuff really is organic, because coal being closer to the surface, yeah, it makes sense. It has these rings and things like that, and it's so much closer to organic material. And the way it's coal comes in a variety of types. And basically, it's characterized here in this chart by the on the x-axis there, the oxygen to carbon ratio, and on the y-axis, the hydrogen to carbon ratio. And basically how it works is with coal is that the lignite on the right-hand side, now that has your lowest energy content, that's around 10,000 BTU per kilogram. And as more pressure is applied and more it sort of goes longer, the oxygen gets squeezed out of that molecular structure, and it becomes what's called bituminous coal. Now you may recognize that word coming in again, that bitumen, and it is bituminous coal is sort of akin to oil sands. If you look at the picture in the notes, it sort of looks like, tarry sand that's been clumped together. And then it's finally, as you squeeze further, longer and longer, you eventually get to anthracite, which is very close to pure carbon. And in fact, you can chemically analyze coal as simply burning carbon using that equation. And it gives you sort of close to the right answer for anthracite, and you can use it as an approximation for for the coal. Just sort of imagining that even if it's that other types of coal, when you burn it, the carbon sort of frees up and reacts with oxygen to give you CO2, and that's pretty easy to do the reaction balance, right? One C on the left and one O2, and then a CO2 on the right. And you can do the same thing that we've done before with the bond energy. So you take the the CO2 on this side, and you subtract, going that way, the O2. Now, what do you do about the carbon? Okay, carbon is seized there by itself, and it's like, well, what do we do there? And the way you have to think about that is that it starts as a solid, and if you remember your chemistry, carbon is group 4. Oops. All right, so let me draw a carbon matrix. All right, and there's a chart like this in the notes. I'm trying to figure out how to, and I notice my focus is not perfect, and I apologize for that, but I don't want to mess with the camera. I'm trying to figure out how to scroll on the screen without it going out of focus. I do apologize for the focusing issues here, and I am planning to go to Staples later today and see if I can find a different camera. If anyone has a suggestion for a webcam, please let me know. Anyway, the way to think about this reaction is you're starting with solid carbon, which is, because it's group 4, remember your chemistry is bonded on all 4 sides. What you want to think about in terms of the bond energy is how, of course, the bonds are CC, and you want to think about how many carbon-carbon bonds are required per carbon atom. And if you look at this, this is a picture of 24 carbon atoms. And so how to think about how this breaks up into individual carbons that can then react with oxygen is to first think about breaking it up into pairs. And so if you took this sort of solid of 24 carbon atoms, and you circled the pairs that I have shown there, that would break it up into sort of this kind of gaseous set of CC pairs. And if you look at it, you can count the number of bonds then that have to break, which is you take 1, 2, 3, 4, 5, 6, and you multiply that times 6, and so you get 36 CC bonds that had to be broken up. All right, think about it again. Okay, look where I've drawn the ovals through. There's 1, 2, 3, 4, 5, 6. So 6 per pair, but you only count half the pairs, so to speak, because when you do the ones that are circled, you get the other ones too. And so that's 6 times 1, 2, 3, 4, 5, 6, 36. So So there's 36 to get pairs. All right. And then, in order to break up all the pairs, now you have then 12 pairs. And so you have to add, all right, I broke 36 bonds to get 12 pairs from this solid. And then I have to break one bond in each pair, so that's another 12. And I'm going backwards here, 48. Can you see that? Yeah, so I had to break 48 carbon-carbon bonds to get one. So basically there's 2 CC bonds on that side. And so in the reaction, you have 2 CC bonds on the left-hand side and plus an OO, and you subtract that from the 2 CO bonds, and you know how to do all this now, and you get 4.35 eV. That is to say, for each carbon atom in your solid, you release in that reaction 4.35 eV. Now, the actual value is about 4.09, and if you then use a molecular weight for a carbon atom of 12 AMU, you get 31,000 BT per kilogram, and so it's very much in line with anthracite. So this all works. All right, so you know, that's how you do the chemical reaction. Now the rest of this stuff is you know, kind of interesting. Read of, you know, where you find coal. It's sort of interesting, even though the process involved is completely different. That where you find coal, for example, in the United States, is very similar to where you find oil and natural gas. There's some notable differences you can see in the charts. You know, coal is typically near the surface. Okay. I find I have to be very careful scrolling. I don't want to lose my focus. All right. Now let's talk about coal. These are the top coal producing countries, and you can see it's dominated by China. So coal. Now the first thing to understand about coal is that it's mostly used where it is mined. And the reason why is it's difficult to transport it because it has relatively low energy content per weight, but and sort of, you know, again there's this image of you know, the guys in the Titanic shoveling coal into the boilers, but so it's not economical to transport it, and so if you look at well, okay, if you look at the consumption of coal, I thought I had a chart here on that, you would find that it is okay. I thought I had a chart there. I mean, basically, you can take this chart of where coal is produced, and it's roughly the exact same chart of where it's consumed, except that Australia is replaced by Japan, because basically a lot of the coal that's mined in Australia is shipped over to Japan. Okay, so you see basically that you know, as we sort of discussed, coal is you know, not used as much as other energy sources in the United States, but it is a, a top source of energy in China. And, you know, that's sort of shown here. Um, China's coal burning has fueled their economic expansion during the early 2000s, and you know it has leveled off sort of, and it's sort of the coal use in China is equal to roughly the coal use in the rest of the United States. Now, part of the reason we're in okay, let's come down to this slide here. What this is showing is the percentage of the U.S. Electricity generated by coal-fired power plants. And part of this is that you know, so you sometimes put, you know, okay, a coal mine. You know, if you had some sort of coal mine there, you would put, you know, a power plant right next to it, and so the coal just basically doesn't have to go so far, and then you generate electricity. And that was a very good working model for many decades. And what you can see is that starting around 2008, when coal plants, you know, they supplied nearly half the electricity in the country, in the United States, and that's been steadily declining over the years. And on the same plot here, I show the reason why. Natural gas's percentage of electricity generation has been steadily going up, and then the difference is made up in as we'll see, in wind and solar. And but it's been primarily this picture where coal-fired power plants are replaced with natural gas plants. Now, you guys know the reason, basically. Starting around here is when fracking started. And so, as we'll show when we cover natural gas, the production of natural gas started skyrocketing around 2008, and so the price of natural gas went down, and so because and became comparable with that of coal, and so the because it's so much easier to run a natural gas-fired power plant. Again, imagining, you know, the guy shoveling coal in the Titanic versus, you know, opening and closing a valve for natural gas. That utilities much favored using natural gas over coal. So part of the point of this chart is that I want you to recognize that this displacement of coal use by natural gas has very little to do with regulations. It is almost entirely an economic picture, and so coal regulations occurred, you know, much later. You've heard some things about Clean Power Act and stuff like that that occurred, you know, later than 2012. And so what you can see here is that this is a phenomenon that's been ongoing for some time, starting with when fracking started. So this is a very natural, technological and economic picture of what's happening here. And so the percentage of electricity generated by coal in our country has dropped down to around from when it was around 50% by half to about 25% today. Now, okay, so you may think to yourself, well, why are we talking about coal then? Because, you know, it's going away. And, you know, we'll talk about, you know, we'll touch upon climate change and global warming and why coal is sort of worse to use as a fuel in that regard. But this is the reason why we're still talking about it, which we can, I can blow up this chart a little bit maybe. What you can see here is that the coal reserves in the United States are around 267,000 million tons. And if you, I think I have it here. Okay, unfortunately, yeah, okay. So this is in billions. So the way to think about this is that this is 267. Oh, I lost my focus. Okay. That worked. All right. So the way to think about this is that if I can get away with pointing here, that is approximately at our current consumption rate, 267 years of coal, and so there's a lot of it in the country, and you know, we can, and so it's anticipated that if other sources, quote unquote, run out, particularly petroleum, that in this country we still have a lot of coal, and the technology is all there to mine it. We could easily increase coal production, you know, almost as much as we want to, and so in the event of dire straits, you know, it can be treated as an energy resource, as an available energy resource, and that leads us to coal to liquids. Now we start to have a discussion, our first sort of real discussion of energy systems. And you know, in your final project, you will have a line for coal. Meaning, okay, how much coal we use in the year 2050. You can put 0 if you want. I mean, but you know, again, your final project is not meant to take into account global warming, and so I mean, you may decide that coal is a resource that we will be exploiting in the year 2050, and so there's sort of two paths for its use. The first one is the way we're using it today. Okay, we generate electricity with it, and so as you'll see in your final project as we go through the course, sort of the linchpin in our energy system is transportation, and so electric cars. Now the other route is shown here. We can make synthetic fuel. I mean, I just put fuel. You understand that's gasoline, diesel, and we can then burn that, and I'll write internal combustion. That's a term we're not, you know, using yet, but regular gasoline or diesel powered cars. Let's talk about a little bit about the chemistry because it's kind of fun. This is called the Fischer-Tropsch process, and basically how it starts, that synthetic fuel, is you sort of have a big column, and you put in coal dust, and you sort of, from the bottom, put in steam, and so you can see that as the coal dust falls and the steam goes up, you're reacting that coal dust with water via the steam, and you're producing hydrogen gas and carbon monoxide. Carbon monoxide is termed in this reaction, what is it called? Okay, well, let's just call it carbon monoxide. There's a term for it there. But so part of the reaction is to do that. And then you take that carbon monoxide, and you react that carbon monoxide with the hydrogen you've also produced. And so you then subsequently produce alkanes. Now this is an endothermic reaction, of course. I mean, we're building up energy into our chemical. The water is a byproduct, I guess, that falls down in this reactor. There is what's called the water shift reaction, because you have to take and get an extra CO up in here if you go through it. But basically, this sort of process, I imagine, this was, I think it was invented in World War II in Nazi Germany because Germany had large amounts of coal, and so they needed to start running their tanks on something, and so they learned how to make alkanes from coal, and I imagine there was some experimentation basically with this sort of column structure and pulverizing coal and blowing it downward while blowing steam upward, and then collecting alkanes, and then you start futzing with it and maybe putting in some oxygen here and stuff like that, or more air. Probably you adjust the airflow and you get it just right so that you're producing diesel, or I mean basically here N can probably be varied to get you what you need. Oh, there's my water shift reaction. So on an overall basis, okay, oh, that's right. I just have to tell you. Oh, here we go. I'm sorry. There's a link. So let me make this a little bit smaller here. That if you go to this link, which I think still works, it'll show you that coal to liquid refineries. Now there aren't any in the United States. There's the main ones are in South Africa now. That you get about 1.6 barrels of oil, alkanes, per ton of coal. And if you did that chemical analysis and took the density of coal, you would find that a ton, that's 2,000 pounds, so this is English units, is about 20 million BTU, and a barrel is this. And so this is, at least from that one reactor, 45% efficient. So let's get back to our picture here. On the one hand, we can take the energy content of coal and we could generate electricity like we currently do. And what you're going to see is that then that's about a 35%. And what I'm going to start doing is I'm going to put a efficiency here in this way. Let me do it on the other side so that we don't get confused. So when you take coal and you burn it in a power plant, and later we'll learn how that works. You get in the electricity 0.35. Okay, you get 35% of the energy content of the coal in your electricity that's distributed then in the country, roughly. I mean, um, now then, an electric car, we'll see, is about n equals 0.8. Let me do it on this side. There's a wall here, and that's why I can't scrunch up further. Okay, so this path, the overall efficiency is 0.35 times about 0.8. And so that works out to around 24% conversion this way. Okay, now this way, as we've seen, to make the synthetic fuel, that's about a 45%. So the efficiency of that conversion is about 45%. We get out 45% of the energy in the coal in our synthetic fuel. Now, here, we're going to spend a lot of time talking about what that number is. Because, and you'll see that your first homework problem this week is to, a sort of first order approximation to figure out what that number is. Let's use 25%. Okay, and that's because an electric motor is much more efficient at converting electricity into work as an internal combustion engine. And we're sort of jumping ahead in the course, but we have to talk about coal starting right now. And so we'll explain these two numbers better as we go through. And so basically this way, you take 0.45 and you multiply it times 0.25 and you get roughly 11%. Now the number in the notes may be a little bit off from that. But you get, and when you go through this process, you get less than half than you get this way. Now, let's talk about the two possibilities here then. On the one hand, on this side, right, we're already doing this. I mean, that's what we do with coal. We turn it into electricity. But we have to drive electric cars. We sort of alluded to the fact in the last lecture that electric cars suck in the sense that they take a long time to charge up. Now, the guys at Tesla and such are working on that and making that a lot better. But as we illustrated in the last lecture, when you pull up the Wawa and you plunk that gas pump in your gas tank, you're getting the equivalent of 6 megawatts of power in the flow of that gasoline. And as we go through electricity, you're going to see that getting 0.1 megawatt of electricity, 100 kilowatts, is a big deal. And so it's just sort of inherent that it's going to take always longer to fill up, so to speak, an electric car. I know a friend of mine has a Tesla, and I mean, when you have an electric car, you plan very carefully when it is that you're going to charge it up, and it's the sort of thing that a lot of people have no problem with. A lot of people have no problem going, now, all right, I know myself, okay, even me, who, sort of a nerdy engineer, I'm like, okay, I got to drive to this meeting in Philadelphia. And so I get in my car and I go, oh, I got to fill up with gas. I didn't think about it, all right? And so what do? I slide into Wawa, and 5 minutes later I'm on my way. It didn't affect me at all. Now, if I had an electric car, I couldn't get in it and go, oh, darn, I got to fill up. Because then it's like, okay, 2 hours later I missed my meeting. So, the question about, this is, there's a big question mark here. And so, part of your final chart in the year 2050 is having to consider, well, are people really doing this in mass. All right, I'm not going to scroll back, because I'll lose focus to our spaghetti chart. But in your spaghetti chart, that very, very thin line coming from electric transportation right now. It sort of seems today to be more than it is, because you hear so much about electric cars, but actually it's a very, very, very tiny fraction of the total vehicles on the road. Okay, so this path, okay, now, of course, we're already doing this, so that's easy. We just keep driving our same cars. This step, okay, would have to be built up. We currently have no coal to liquid generation in our country right now, commercially, I don't think. But people know how to do it, and I mean, it wouldn't take that much work to start doing this step. All right, let's talk about global warming a little bit. Okay, so this is what we're going to do as we go through this. Is that I keep telling you in your final project you can't take global warming into account, because I don't want you to. Now, what I want you to understand here. Remember, this was C plus O2. There's a CO2. Well, that's what happens. That's what happens in this step here. All right. Now, if we go back up to our now, I'm not gonna bother making that bigger. Well, but what you see here is that, okay. Oh, that's not the final reaction. That's my shift reaction. This is the overall reaction here. All right, we'll just leave it here. The point being that, okay, when you do this step, okay, I'm not showing everything here. You're making alkanes, okay, and you're also producing some carbon dioxide. But the point here is that you then burn those alkanes here. It's the same CO2 on both sides. All right, that's what I want you to understand here, is that, okay, whichever path you take, all right, here, okay, in this path, all that carbon in the coal turns into CO2 in the electric power plant, and then you have electricity. Here, some of the carbon turns into CO2 in this step, and the rest turns into CO2 in this step. I mean, it has to wind up in the atmosphere. There's no place else for it to go. And so either way, it's the same amount of CO2. All right. This way, you only get 11% of the energy, the original energy. And so on a CO2 per energy basis, there's twice as much, or more than twice as much emitted on this path. So, if global warming, well, it will be. It's not for you in your final project. But if in the year 2050, it's almost certainly going to be. It's very unlikely this path, if we decided we had to use coal, okay, that we're running out of energy, we have to exploit this. Because it seems very likely that we're in the throes of climate change right now, and it's only getting worse, and by the year 2050 it'll be completely apparent that it's something we have to do something about, because this path, for only getting 11% of the original energy, you emit the same amount of CO2. It's unlikely on that basis. All right, and so this is kind of a weird thing, because I'm telling you that to not take that into account, okay? Because it's sort of too complicated for you to do in your final project. So you can choose either path, and there's a line in there for either path. And as we walk through the final project, you'll see that this here is the linchpin, electric cars. And the question of whether there really is going to be widespread adoption, okay? The pulling up the wall business, okay, is, you know, I mean, um, will people in general um, be able to embrace this or not? Because if the answer to that question is no, now why would it be no? I don't, you know, it just, that's a societal question, okay? Can people come to grips with electric cars? I mean, on a widespread basis, there's a lot of questions there about whether, I mean, think of it right now, you know, if you have to pull up to a charging station, there's one available. But if everyone's driving an electric car, well, so, you know, you may decide in your final project that that's really not going to happen. And so you may choose this route to utilize coal. This is, you know, the things I want you to think about. And, you know, basically there's no right answer, because I'm telling you, you know, you're not to use climate change as a as a decision factor here. And so your grade is basically explaining just on an energy and utilization availability basis why you choose what you do. Getting back to electric cars a little bit, and you know, my discussion of you know, my supposed meeting in Philadelphia that let's say after I do this lecture I have to go to, and I have to be there in an hour, and I've forgotten. I have an electric car, and I've forgotten that I didn't charge it, so I missed a meeting. So that's an illustration where you have to take into account that choices in your energy system can impact economic output. Okay, which, you know, it's kind of a complicated scenario there, because it's like, well, did I really reduce my overall economic? Maybe I didn't pay for the meeting, okay, or maybe I lost a contract because I didn't attend the meeting. And so, you know, economic output can go down because of the energy and energy utilization choices that we make. And so this is a very complicated question. There are no simple answers here of what we do. Okay, so that's it for coal and the things I wanted you to understand about that. Now we'll sort of circle back to natural gas, because that's going to be your third homework problem. All right, so you know all about this now. Oh, see, I can't do that. Let's see if I can. It looks like it really did it bad this time. Let's see if we can do it. Look at that. Okay, now the question is whether when I pull it down. Hey, okay, I'm learning tricks. All right, good. So I don't have to like do this in two parts again. All right, so natural gas. I'll turn off this light. You know all about it. It's alkanes, N equals 1, maybe a little bit of N equals 2 mixed in. And I wanted to extend your homework assignment just a little bit here again to impress upon you that if you are thinking about global warming, all right, you can calculate, and this is along the lines of what we just talked about, the energy release, and you can calculate it a different way. So let's go back up to our alkane here. you guys in your homework calculated the energy release per weight of alkane. That's your mass specific energy density. All right, now you can do this a different way. You can calculate the weight of CO2 released into the atmosphere divided by the energy. So you start with the number n divided by the energy released, and you can convert that then to kilograms of CO2, and you can convert EV to kilowatt hours. Actually, that's one thing we forgot with units, and we should walk through that a little bit. Okay, we haven't talked about the kilowatt hour. Let's talk about the kilowatt hour real quick. All right, you all know what a watt is. That's a joule per second. Okay, a kilowatt is 1,000 watts, so it's 1,000 joules per second. All right, a kilowatt hour is a unit of energy. It's a kilowatt, so this energy is equal to power times time. And so a kilowatt hour is a unit of energy. It's equal to 1 kilowatt times 1 hour. But that's 1,000 joules per second times 3,600. Remember, an hour is 60 minutes times 60 seconds, 3,600 seconds. So 1 kilowatt hour is equal to 3,600,000 joules. All right, that's pretty simple, really. Once you understand what it means and everything. So you just take 1,000 joules per second times 3,600 seconds. All right, so that's a kilowatt hour, and that's how the conversion's being made there. You first convert from EV to joules, and then from joules to kilowatt hour. All right, so that little backtrack on units that I had forgotten to do. What a kilowatt hour is. Let's go to our table here then. So you do that like you did in the homework too, sort of backwards or upside down. You put energy on the denominator and weight of carbon dioxide in the numerator, and this is what you get. Okay, this is two ways. This is pounds and this is kilograms. Sometimes it's listed in pounds. But just the important thing is to look at the ratio of the numbers here. Methane, you get 0.2 kilograms of CO2 every time you generate a kilowatt hour of energy in the reaction, whereas coal, you get about twice as much. And you know, that just comes from going through the reaction. Part of the way to think about it is that I mean, I don't know if it might help you a little bit. See, here, CO2, there's nothing else on the right except CO2. Whereas for the alkane, part of the reactant is water. And so some of the mass is winding up as water. Some of the oxygen mass is winding up as water. And that's a way to think about the fact that with coal you get more CO2 per power generated. So, you know, this isn't, you know, again, not a consideration for a final chart. This is sort of, you know, so you understand why, you know, coal is bad for climate change. All right. So let's talk about natural gas for a little bit. So we sort of, you know, transportation, you know, as we keep coming back to, is kind of the linchpin in our whole energy system model. What are we going to drive around? And we've talked about, okay, there are various options. I'm going to, write ICE, that's for internal combustion engine. That's our standard cars right now. And that can include gas, petroleum. Okay, it can include, for example, coal to liquids. All right, and over here's electric. And there's no categories there, kind of. An electric car is an electric car. Over here in internal combustion engine, there's a third possibility, which is compressed natural gas. And so, and that's what CNG stands for, compressed natural gas. There's these sort of four options. There's also ethanol, which we'll talk about when we cover biofuels. Sort of five options here for what kind of vehicles we're going to drive. We can drive our standard petroleum cars. These are kind of connected, right? Because it's the same car. We're just getting the fuel from coal. So these are kind of the same. There's electric cars. There's ethanol cars, which we'll talk about when we cover that. And then there's this fifth option. All right, this fifth option is compressed natural gas. And now, if you think about it, there's a question, this Wawa question, right? Because, okay, Wawa, check because, it's still alkane. Check because it's still a liquid. No, of course not. And here, kind of, maybe. All right. Here the problem is, you can't just, go sliding up the Wawa and get 6 megawatts of electricity. At least no one's anticipating that. And so no matter how you cut it, when you quote unquote fill up your electric vehicle, you're going to have to kind of hang around for a while. All right. Maybe just a half an hour, depending on how much further you have to go, but a lot longer than 5 minutes. Yeah. And now compressed natural gas is what it sounds like. It's the volumetric energy content of natural gas, since it is a gas, is very small. And it's 1,000 BTUs per cubic feet. And so basically, if you think about it, we've already gone through this. Here there's 124,000 BTU per gallon. All right. Whereas here, let me keep that. There's 1,000 BTU per cubic foot. All right. Now, a cubic foot and a gallon aren't the same size. The gallon's actually smaller, but you get the idea. All right. On a volume basis, this is a problem. So you have to compress it. And I'm going to write a homework problem for homework 3 where you have to kind of figure this out. And so filling up a compressed natural gas vehicle it's not like plunking that filling handle into your tank like at Wawa, but it might be something close, okay? Because basically what you would have is you would, instead of just plunking it in, right, it would have to attach to your tank. Now your tank has to be a lot heavier and more solidly constructed to take the high pressure gas inside of it. And so, I mean, Do people do it? Yes, they do it. They do it usually for fleets like of buses and things like that. Um, I think there's fleets of commercial vehicles where they have natural gas filling stations. But basically, uh, now there is a precedent here. Um, it's the same sort of issue when you fill your barbecue tank with propane, right? You have to have a sealed fitting connected in there. You don't just, of course, propane is a gas at room temperature and pressure. You have to pressurize it. So there has to be kind of a sealed fitting under pressure. Here it's more of an issue because it's higher pressure. Um, so it's like, okay, well, will people do that? Will people be comfortable with that? As we sort of alluded to, we have lots of natural gas, probably a lot more than we have petroleum. So, you know, this is an option. Now, right now, um, I'm good. All right, this is all about natural gas. Of course, natural gas is the same as oil and where it is and stuff. This chart shows, the advent of fracking in the year 2005, 6, 7. Same sort of story as with oil in the United States. Um, fracking, it took off because we had this new source to exploit. I'm not going to talk about frozen methane. What I'm getting to is down here. You can read all this stuff, it's fun. Okay, this is how natural gas is used. Natural gas is a sort of more versatile energy source because we use it to heat our homes and our businesses. We use it in industrial processes, and we can use it to generate electricity. So natural gas has a lot more versatility, and we can use it in our vehicles. All right, and this is the use of natural gas in vehicles in trillion cubic feet per year. So I'm going to make a quick conversion here. Natural gas vehicles. So as you can see, it's somewhere around 0.05 trillion cubic feet per year right now, and we've gone through that. This translates. This is equal to, in quads. So it's much, much less than the petroleum, which is about 30 quads. Okay, hardly any. It's just like electric. It's very minimal. And the reason is, probably has something to do with, okay, the complication. I mean, the engine's roughly the same. It's not a very much different engine involved here. It's an internal combustion engine. You do have to make some slight modifications to allow the use of a gas fuel as opposed to liquid fuel. But in fact, in a way, it's kind of simpler because when you have a liquid fuel engine, you have to vaporize the fuel before you can use it anyway. So it's, to a certain extent, the engine's simpler. But yeah, it's hardly, this is, gas diesel, and so it's around 30 quads and much greater than the 0.05 of natural gas. And this is probably because filling is difficult, requires high pressure fittings. It's not just plunking that handle in there. It's like, making some, and they probably have invented that, so it's really not difficult. I mean, you could slide up to Wawa, you know, with if they had compressed natural gas there, and make this sort of seal and connect it in, and you know, load your credit card in, and actually I don't know the filling rate, but probably it's pretty fast, similar to gasoline, and so it has the speed option of refilling your vehicle, but there's this high pressure, and so you know, I don't know whether that's an impediment or not, but it's something to explore, and it's something for you to think about in your final project, and I'll leave it at that. All right, so that's the lecture for today, and we'll go from there.